So far, we've talked a lot about um, using existing fields. So things like density, temperature, and so on. And in fact, earlier when Stephen and John were going through, they talked a lot about, how to do projections of density and whatnot. But at one point, I think you might have noticed that they started talking about actually velocity magnitude, which is a derived field. So what I'm going to talk a little bit about, and this is going to be much slower paced than my first talk this morning, where, as you might know, I was a little, you might have been able to tell I was a little amped up. But this is going to be more slow and sort of interactive, talking about the idea of creating new fields. Because one of the things that we often want to do is we want to take existing fields on disk, these primitive quantities, things like, say, the density or the thermal energy or the velocity, and create other things from them. One of the examples that I use in my own research that actually I didn't put up in here is you can do things like you can look at the declination from a vector that you specify. You can look at specific entropy. You can look at a variety of different things. One particularly fun one was that since a lot of my research has focused on the formation of the first stars in the universe, which are governed by the way molecular hydrogen forms. One thing I have done is I've written several relatively complex derived fields that describe the distance from equilibrium as a function of density and temperature and so on. And what you do is you essentially just write a small kernel, and then this gets applied everywhere, and it spits out a whole new field that's exactly, that's still a first-class citizen, just like anything that YT might find on disk. So I'm going to start off very slowly with a couple, I guess, pedantic exercises, and then we'll try to end a little bit quicker with field definitions and so on. So just to start out, just so we're all on the same page, when I talk about fields, and I know we have a couple particle people in the room, but when I talk about fields, I'm referring to a fluid quantity, and so in grids this is relatively easy to visualize, but I'm talking about a fluid quantity that is defined everywhere in the simulation, where fluids or particles might be found. Like, if you have a simulation, density is going to be defined everywhere in that simulation. Every single grid vertex will have one, as well every grid cell center, and so on and so forth. This is part of the fundamental quantities that are evolved through the calculation. Usually in simulations, and I know Flash and Enzo evolve the energy somewhat differently, but you have a variety of primitive quantities that are dumped to disk at every single time step, and then perhaps during the course of the simulation others are added on. In YT we have this concept of known fields. These are fields for a given type of simulation, a class of simulation that it knows might exist. So for instance, I'm going to rely here on both Enzo and Flash. The idea is that sometimes in an Enzo calculation you might have molecular hydrogen density. Sometimes in a Flash calculation you might have density of, I guess, magnesium or something like that. You might have all these different things. So these are known fields. YT knows about them, that sometimes it might find them in an output file. They might not always be there, but it can add on to these the idea of, oh, these are the units. If you want to take a line integral, this is the conversion factor you apply once you get through the simulation. You ought to log these in general, things like that. And then there are these ideas of derived fields. So this is a function that transforms on-disk fields. So this might be a mechanism of taking out density and temperature and getting the rate that dinosaurs would be created at that field, at that cell center, for instance. That was expected to get a bigger laugh than it got. I was saying that for the YouTube video. So some common fields that are used in YT, and these cover a number of different use cases, would be density, temperature, the velocity along different directions, and the cell mass. Now the thing about cell mass is that, as you might know, cell mass is just the product of the density with the volume of the cell. And so volume is also in there. There are a variety of different fields that you can use, and this one is a composition of existing fields that are on disk, or that are known to YT that it can calculate from the grid. So cell mass only depends on density existing on disk, but it also depends on knowing something about the grid patches. It needs to know the size of the individual cells. So one thing that we've relied upon through this is that YT also performs a regularization of names through aliasing. So when you ask a Flash data for cap DENSITY, it actually knows on the back end that it should instead fetch lowercase DENS from the HDF5 file. This also happens with the other data sets as well. Like for instance, boxlib-based data might have a different mechanism referring to internal energy or density and so forth. And what it does is, while you can still access those by their original names, you can also access them by some alias. And I'll show you how to query a given data set for the aliases and for which fields are available. So, a couple of these would be like x velocity translates to velx in Flash, density to lowercase dens, temperature to lowercase temp. You can actually, if you want to look in the the source code for which fields are aliased, you can find it. And this is a good usage of what Cameron showed you earlier about how to navigate the source tree. So now the question, how do I find out which fields that YT knows about? Specifically, how do I find out which fields YT thinks it can find on disk, which fields YT has found on disk, and which fields YT thinks it can generate in memory? So if we take a look, this is just a very simple script running on Enzo 64, and I would recommend that everybody do this. So let's just, you can also do this with a Flash data set. So let's start up a Python session, type from yt.mods import star. This is also done for you by default if you run IYT. So if you just type IYT, you can skip the first line. Then you load up a data set, and it doesn't matter which one. I've done Enzo 64, but if you want to see a whole bunch of fields, try Isolated Galaxy, which has a whole bunch of magnetic fields as well as ionization fields. And then take a look at pf.h.fieldList, and then I'll walk you through what it's doing. So what YT does when you start up is it loads up this parameter file, and then when it loads the parameter file, it gets a number of very lightweight characteristics of the simulation: domain size, time, redshift, whatever. Then when you ask for the mesh, this .h, this hierarchy, which we've talked about a couple times, which is the heavyweight object, it goes out and examines the data that's on disk. For an Enzo data set, it randomly examines, n grid patches that exist on disk. It takes the union of the fields that it finds in each one, and then it processes those, and it says that those are the fields that it knows how to find on disk. Flash's data format's a little nicer, so it's able to just look at one and take all of the fields that it finds in that Flash data set. The same thing for boxlib-based data. Yeah, that's correct. It ensures that the random sample includes grids with particles in Enzo. This was a problem for star particles. This was recently changed, and the problem. So that problem exists, or it existed up to version 2.3, and the only time that it would show up is if you had a simulation that had star particles but no dark matter particles. Or at least that is the only time that it was likely to occur. Which is much more common with non-Enzo or with non-cosmological data sets. Most cosmological data sets, do have the dark matter. So was everybody able to successfully examine pf.h.field_list? Anybody have any problems with this? No? Okay. Did anybody use Isolated Galaxy? Yeah, how many did you find in that? Oh, the response for the video was, oh Lord. Couple dozen. Yeah, 35. Okay. So now these are all the fields that it knows exist on disk. So the examples here: particle type, temperature, gas, energy, density, creation time, particle index, z velocity, y velocity, on and on and on. So now there's an auto-generated list of all the derived fields that YT knows about, which I'm going to discuss in just a second at docs 2.3 reference field list. If you just go to the documentation and click on reference, you'll see the field list. And in fact, for the derived fields, that field list includes things like the source code to generate that field, the units, and so forth. So now let's take a look at derived field list. So if we do for field, and actually if you still have that session open, just look at pf.h.derived_field_list. So this list is actually probably a lot longer, right? I mean, I would guess there's at least 100 for this. Is that the case? So when it examines the file and it calculates all the fields that it can find on disk, it also goes through every single derived field that it thinks it can generate. Every single one that it knows that IT knows about. It finds these inside the output type specific derived field list. It finds them in universal fields, and it can find them in your plugins file. So in all of mine, you can actually see that /home/mturk/.yt/myplugins.py gets loaded. That file actually just gets executed every time you start up YT. So this is a place you can stick things like commonly derived fields, or if you don't want temperature to be logged, and so forth. This is a place you can put it if you want that to be the case every single time. So it has this gigantic list of potential derived fields. And what it does is, using the fields that it finds on disk, it calculates whether or not it has the dependencies necessary in order to calculate that field. For instance, there's a molecular hydrogen fraction field, which relies on both a density and a molecular hydrogen density. So that field will show up in this list if you have both density and molecular hydrogen density in your data set. And if you do not, it won't show up in that list. It actually goes through and tries to generate that field, and if it is able to do so successfully, then it adds it to the list of derived fields for that data output. And if it is not, then it does not add it to it. So in this way, you can get an idea of all the possible fields that you can examine from your data set. Now these lists are just strings. But if you take a look at pf.field_info, that will be a dictionary of field objects. These are objects that carry some piece of information or set of information about the fields. Things like, should it be logged? What are the units? What are the conversion factors? How do I integrate this spatially? And so on. So for instance, now you have to remember, because these fields only get added when you create the mesh, if we load up enzo64dd0030/data0030, we do pf.h, we can then do pf.fieldinfo density and get units. And it spits back out a LaTeXable piece of unit information. In this case, grams per centimeter cubed. So we know that density is going to be in grams per centimeter cubed. Now additionally, we've got this mean molecular weight field. We want to see what the source code is for that. In this case, the source code for that is define mean molecular weight, except field and data, return density divided by the mass of hydrogen times the number density. So in this way, you can inspect both how the fields are generated and which fields are available, what they're expected to be, and so forth. Now, as I mentioned, the units are typically expected to be in CGS, and what we try to do, and we notify you if we are not able to do so, is to calculate the unit self-consistently from the file, and then translate things as they are read in from disk. Has everybody tried doing pf.fieldinfo and looking at one of those? Anybody having trouble with this? No? Okay. So now let's get on and let's start defining our own field. In this case, we are going to try defining the dinosaurs field. There is a particular idiom for generating a new field. Now this is using some Python syntax that may not be completely familiar, but what we do is we start up from yt.mods import star, and then we use this little @ symbol. We say @derived_field, then we give it a name, and we give it a unit. You can specify other things as well, which I'll go into. And then you define a function. We'll call this function dinosaurs, and these functions all have to accept the same type of arguments, and they always have to return a particular type of object. In this case, in all cases, you have to accept both a field object, and this will be an actual object for your field, and data. Now data can be a grid patch, it could be a slice, so it could be 1, 2, or 3 dimensions. So typically what we do is we operate like this is just a fully local kernel. Now what I'm doing here is inside this function, I take data density. I'm not sure if anybody here has taken paleontology recently, but dinosaurs go as density to the 2/3 over the square root of temperature. So what we're doing here is we're taking density, we raise the density field to the 2/3, and then we divide it by temperature to the 0.5, and we return that value. Yeah. It does not. Oh, sorry. The name of the function does not have to be the same as the name of the derived field. And the reason for that, Cameron, is that if you prefix something with an underscore or 2 underscores, it will not be exported in an import statement. So you can hide the actual underlying functions and only give back the fields. It's not terribly crucial. And so now, once we have done this, and actually I'm going to jump to another window. I know you can't see what I'm typing, just a second. So now, here, let me... If I define something like at derived field name equals dinosaurs, define here. At derived field name equals dinosaurs, units equals T-rex per second. Yeah, I know. It should really be T-rex underscore fraction. That got a laugh. This is on the isolated galaxy. And now I don't know if you remember, but earlier we did this all data. And what I'm going to do is I'm going to collect all data, which is the entire box. Crumbs. I'm going to collect all data, which is the entire box, and then I'm going to just print out dinosaurs. And you can see that it prints it out, and we're generating, that sounds about right, 10 to the minus 23 T-rexes per second. So now what we can do is if you take a look at pf.field_info, dinosaurs.get units, it returns to us T-rex per second. So this is an entire object here, and now we can also take a look at this object itself, and it has a number of other things. See, it's an actual object. It has a number of things, like for instance, take log by default is set to true, and we can also print out the source. It looks nicer actually if you print it. So we have access to all of these fundamental components of the fields, even once we've created them. And so in this manner, the idea is that you can compose new quantities out of fields and generate, you know, new types of analysis on those. So are there any questions at this time about defining simple fields? So this is just simple fields so far. We'll get into a little bit more complex fields in a few minutes. So that's called a decorator. And so what it's doing is derived field is something that YT defines. It's a function that accepts a function as well as arguments. What it essentially does is it takes the next defined function as an argument and returns the final value. Basically, it's syntactic sugar, it's called. So it's a simple way of making things look a little nicer. It is fundamentally the same as taking, without the at symbol, derived field with those arguments, and then supplying to that the argument dinosaurs, or the function itself. There's an older syntax that was used in YT that was add underscore field. This is just slightly more concise. So derived field, the decorator can take a number of arguments. It can accept a function, but typically you don't need to supply that, so let's just ignore that one. It can take a conversion function. Sometimes you necessarily need to convert something to CGS. However, keep in mind anything that you accept from the data object itself should already be in CGS unless it is a spatial field, and then it is in the local domain units. So for instance, back here, density and temperature will already be supplied in CGS because they've already had their convert function applied. Units is a text field of units that you can, that is suitable for latexing, and if possible, it will be fed into a math text rendering engine for Matplotlib, which is a LaTeX dialect or a subset of LaTeX. Projected units it's the same format, so it's LaTeXable, but that's the units that you would expect after taking a line integral with this. So if you take an unweighted projection, these are the units that should come out. This only shows up once in a while. Typically, density is the one that you see most often. Density has units of grams per cubic centimeter, but projected units of grams per square centimeter. So it's that sort of thing, because you integrate through centimeters. Projection conversion are units to multiply against after you project through the domain. So if you wanted to get something that was in, say, per kiloparsec, you would just change that. Take log is things like, should we tend to take the log of this? So this governs things like how do we set up color bars, how do we set up the bins for 1- and 2-dimensional profiles, should they naturally be taken log? Like, for instance, density, of course, you want to take the log. X velocity, not necessarily, since you can have negative values. Particle type, is this field shaped like particle data or fluid data? This governs whether or not it's expected to be 3 dimensions when it comes off of a grid patch. The display name is a nice LaTeX-friendly version of the name. So this could be, for instance, if it could use math text to write something. It could be row if you wanted it to be for density. And validators are mechanisms of requesting and requiring more information about the field. And that's in fact what we're going to talk about next. What's a validator? So there are 4 defined validators in YT. There's validate parameter, validate data field, validate spatial, and validate grid type. These govern what type of data object is fed in. Now if we go back and we take a look here, I mentioned earlier that data might be 1-dimensional. If it were, say a sphere, that data is returned as a 1-dimensional array. It might be 2-dimensional if it's a slice. It might be 3-dimensional if it's a grid patch. So validate spatial ensures that it's always 3 dimensions. Validate grid type ensures that the data object that is passed in is actually an actual grid patch. And the reasons for that might be that you wanted to take a look at the spatial extent of that grid patch and use that as input to the field. Validate data field is typically not necessary. but it ensures that the data set has a particular data field. Like, if it doesn't make sense for you to calculate the star formation rate unless there is an actual star formation field, or a star particle type field, then that would be a good candidate for that. And validate parameter ensures that a particular parameter is set. Now, the question that Molly posed earlier, which actually touched upon this, was, what's the point of having an angular momentum field if you don't have a center? This is how things like centers get passed in. Or what's the point of having a height field if you don't have a vector along which you can define that height? This is how that gets passed in. Validate spatial is the most fun because it's the one that you can also specify a number of extra zones to get. So if you have a grid patch and you want to apply a 3-point stencil to it in order to calculate some sort of finite difference, then that slices one off at the end of each side, right? So what you can do is, if you specify that you would like an extra couple zones in every dimension, and with a validate spatial validator, you can then require that it fills in ghost zones through a cascading interpolation procedure, and supplies to you an extra large grid, for instance, or an extra large 3D array, against which you can then evaluate a finite difference, and then return to it the correct sized array, and still have your field defined everywhere in the domain. For instance, the divergence field, although actually this is delta velocity. So an example here is first we're going to talk about field parameters. So one thing that I've recently had to do when I was calculating some stress tensors was examine the deviation of local velocity from a bulk average velocity. So what we do here is we start out, and this is, I don't know, is this the most complex script we've seen so far? I sure hope so. What we do is we start out with our standard from YT mods import star, and then we define a new field with our @derived field, and then remember just below it you have to have your field definition. Now I'm going to call it delta velocity. Units are centimeters per second, and my validators are that I need a parameter bulk velocity. Oh, sorry. And actually, I've incorrectly used the R, but it's still valid syntax. But R just means that if there's a backslash, don't evaluate that backslash to mean something. It means I'm supplying to you a raw string. So if I give you a backslash T, that doesn't mean tab. That really means backslash T. And the particular one that this comes up with a lot is $sign and %. Now in my delta velocity, I call on the data object get field parameter bulk velocity. So now I have this object bulk velocity. So this, and I show you how one might do this later on. But then I subtract BV0, which is the x component from x velocity, and I square it. Then I add to that the same thing for y and the same thing for z. And then I return delta v. So now below we actually use this field. I load up isolated galaxy, and so you all have isolated galaxy, so you could do this as well. I load up isolated galaxy, and I create a sphere located at the most dense point in that calculation. It's going to have 0.01 megaparsecs in radius. So what we're doing here is I'm saying, just set it at the max density point, and remember we can use a tuple of the size and the unit. Earlier we saw how to do this a different way with dividing things out in order to convert units. And then on this sphere, I call the quantities bulk velocity object. Remember Sam showed you how to do derived quantities a little bit earlier. And so this gives me the mass-weighted average velocity of that 0.01 megaparsec sphere. Now I create a new sphere, also at the max, but this time I want it to be 100 times larger in radius. So it's 1 megaparsec. And I set the field parameter bulk underscore velocity to be this bulk velocity that I calculated earlier. And now I print out the min of the delta velocity and the max of the delta velocity. And so that means now that up here inside my field definition, I can call the get field parameter bulk velocity, and I get back this value that I calculated off SP small. Now there's a reason that we're doing all this in somewhat of a complex fashion, which is that by using this set field parameter rather than just passing things in, I can define this field once and use it multiple times on different objects just by changing the parameters that are passed in, rather than going through and calculating it manually and passing it in. This can be a generalized field that I use multiple times with different data sets. Additionally, Sam will talk a little bit about this tomorrow, but this plays nicely with parallelism if we use it this way. Yeah, sure. Yes, that's correct. So what Cameron said was that what the validator does is require that that parameter is set for the data object. And if it doesn't, then it will error out, and it will actually tell you this is required. So if we were to run this without having set the field parameter bulk velocity, it'll throw an error called needs parameter, and it'll say needs parameter bulk velocity. So then you'll see this, and you'll say, oh, I need to supply a bulk velocity because a delta velocity doesn't mean much without that. Nathan. That is... that's true. So it's interesting. The validators always throw an exception, but YT doesn't know how to catch the bulk velocity exception, and so it gets passed to you, the user. But YT does know how to catch a spatial exception, and so then it fixes it. So it's like different parts of YT fighting against themselves. No, I'm kidding. Sure. So Nathan asks, he's seen 3 different mechanisms of passing data into a derived field. One of them is where he gets a one-dimensional array, like say a sphere, and another one is where it's specifically a grid patch that's 3D, and the third one is where he gets a 3D one with all integers. The third one is actually the field detection. So that's when it's trying to figure out if it can generate that field. For those cases, they may require a little bit of massaging, but the reason that you want to get that is so that that field shows up in the derived field list. Yeah, returning inside there should work as well. Yeah. Okay. So now this is the output of that. Now if you look down here, you remember this is the delta velocity min, delta velocity max. And what it's doing is it generates it, calculates the bulk velocity, sets the bulk velocity, and then requests delta velocity. And then it spits this back out here at the bottom. So now spatial data. This looks a lot more complicated than it is, so we're going to walk through this. But what you can do is, again, you can calculate an average, for instance, that is over some fixed width of cells. So in this case, we're setting up a derived field of name averaged temperature. Validators, a validate spatial. Now, you remember back here, I called validate parameter, and I supplied to it the name of the parameter that I wanted. In this case, I'm supplying to it the number of extra zones in every direction that I want it to generate. Okay? And so I'll explain in a second how it generates those zones. But I'm saying that I want one extra zone. I'm going to shave off one zone on every single side. So now, inside my function, first I calculate nx, ny, and z, and these are the shape of temperature. And then I create a new field, which is that shape minus 2, because remember we're going to be shaving off one zone on each end. And my weight field. And so now I simply, I'm going to calculate a slice that slices it off in every single direction, multiply it by my weighting field, and then I return it to the other, and then I multiply it by my actual field. So in this case, new field plus equals data temperature sliced times cell mass sliced, and the weight field plus equals data cell mass slice. So this slice object is a Python object that goes from I to nx minus 2 minus I. And so this is just a terse way of taking a slice on every single dimension. There's a more verbose way of doing this that will be in the narrative slides. And then this new field 2 is NA zeros of nx, ny, and z, and I fill it with the new field divided by the weight field. So in this way, I've calculated an average temperature at every single one. Now it's okay for the new field that you return here to have an extra zone of zeros on every single end. And then, I calculate my sphere at 100 kiloparsecs, and I return that, and I print out that data. Yeah. Yes. That's so that it doesn't get exported from an import of this. It's just to hide that function. There's no real reason to call this function outside of requesting it like this. And so by prefixing it with an underscore, we're just saying, don't bother. Now this YT comes with a couple things that use spatial fields, like averaged density, divergence. I think there are a couple magnetic field items that use this. But I think also there might be a gradient field somewhere. So now how does it generate the spatial data? Now we want to make sure that we are numerically, that we have numerical fidelity here. So I wanted to explain very briefly how it generates these extra zones. It's not like these zones necessarily live on disk. Typically they're carried around as boundary conditions during the course of a simulation, but then they're not written to disk always. With some codes, it does write them to disk, and for those codes we use those zones. But first we identify the level at which the region you're requesting is fully contained. So that would be this grid plus n zones in every single direction. And then it fills from the grids at the lowest level, that tessellates that domain. Then it interpolates to the next level, interpolates to the next one, fills, interpolates, fills, interpolates, fills, until it gets up to the level at which you've requested it. This method is actually in the code, and I would be happy to go over it with somebody. But the idea here is that what you want to do is you want to avoid grid artifacts, and you want to avoid what's known as hanging nodes. Hanging nodes are where you have greater than one jump in refinement between boundary conditions. And so by doing this cascading interpolation, typically you avoid that. This is also the method that's used for volume rendering. And so it applies it's strictly speaking known as a crack fixing technique, as well as this technique. So now let's talk briefly about how one might generate derived quantities. Now first we want to talk about derived quantities, but somebody took this slide. So you've probably already seen this slide. But essentially a derived quantity is some reduction of a fluid quantity into a fixed set of numbers. So this would be like the angular momentum vector, or the average density, or something like that. Basically something that processes the fluids into some other value. These can be computed on any data object, and that's kind of a cool and important thing in the sense that you can calculate the same quantity, like an angular momentum vector, on a torus or on a sphere or on a cylinder, and it operates in exactly the same way. So now to access these, as Sam showed earlier, you can just do this dot quantities, and then say center of mass, and then it'll print it back out for you very happily. And there are a number of quantities that are already defined, things like total mass, center of mass, angular momentum vector, bulk velocity, total quantity, and weighted average quantity. Now the idea here is, very, very common idiom is to use these as inputs into a field parameter. So, for instance, you might use your angular momentum vector in order to calculate the declination from your, from the fundamental pole of your disk, or something like that. Or you might look at your bulk velocity. You want to take a look at your radial velocity, and so in order to calculate radial velocity properly, you need to subtract off any peculiar motion of your central zone, for instance. So, for instance, here we have a radial velocity parameter. So we've got, for instance, isolated galaxy. We calculate our bulk velocity on our small sphere, and then we set our bulk velocity value, and we calculate the extrema of the radial velocity. Now, I guess I screwed up the script here. But then you could calculate the radial velocity extrema without the bulk velocity set, or with the bulk velocity set to a different value. And you can see that the radial velocity will actually be different because it gets processed differently inside the fields. So this works for data object, but for volume rendering you have to be a little bit tricky. Like for instance, if you want to volume render something like the the declination from a value. Now keep in mind we use the word volume rendering to describe as well any traversal of the grids along an axis. So while you may not want to visualize something like that, you may want to calculate a weighted integral. So if you want to do like Tumre Q or something like that, you need to set field parameters. And we'll go over in a couple days how to pass field parameters into fields for volume rendering. Common field parameters are center, mu, bulk velocity, and height vector. And in fact, these are the only ones that you would need to manually set. And center is usually set by a data object. So if you create a sphere, if you create a cylinder, if you create any rectangular prism, it will set the center for you, and you don't need to do it yourself. But you can also override it. Mu is the mean molecular weight, and bulk velocity gets used in things like angular momentum. And the height vector is if you want to do up, and you want to do something like cylindrical radius or height or something like that. Not all codes have that specified. Well, I guess for instance, taking as an example Enzo, if you run something that doesn't have species fields, the mean molecular weight is actually set internally by a pound define, and it's not written to disk. Or at least this was true before 2.1. And so you would need to specify mu in order to ensure control over that function. The question was, why doesn't it know the mean molecular weight automatically? So now, how would one go about making new derived quantities? A lot of this is related to the fact that YT, as Sam will discuss tomorrow, is designed to operate transparently in parallel. And so it requires somewhat more work on the part of the user in order to ensure that objects operate identically in parallel as well as in serial. And so the process for how a derived quantity is calculated is first it goes out, YT goes out, it divides the operation into a couple chunks. Like for instance, if you're calculating the bulk velocity on a collection of grids, it divides the grids up into lists. Each processor owns its own grid. In the case of only one processor, as in running in serial, it gets all of them. Those get spit out to each different one. Each one gets processed into some intermediate reduced value, and then those intermediate reduced values are somehow combined, and then the results are returned. So now, this allows, again, for transparent parallelization, but I'm going to show you how to write one. The idea here is that what you want to do is you want to construct a reduction function that operates on a single object that might, for instance, calculate the bulk velocity of a given grid patch. And then what you want to do is you want to construct a function that accepts the bulk velocity of multiple grid patches, and then you use the function add quantity. So here's an example for total mass. And this is actually from the source code, but it is also in the repository. And I did link to this from the website, so you should feel free to go and examine the source code. So for an example, for total mass, we define this function underscore total mass, which accepts data. And we calculate baryon mass, which is the sum of data cell mass m sun. And we calculate particle mass, which is data particle mass m sun dot sum. And we return baryon mass plus particle mass. Now you always have to return a list from this from the individual object reduction function. And the reason for that is so that at the end these lists can all be concatenated and operated upon. And now we have this multiple list, which is combined total mass, and it accepts data and total mass. And you return total mass dot sum. So now what you can sort of imagine this doing is it goes out and say each one gets, each grid gets distributed to a given processor. Let's say you have 16 processors and 16 grids. Each one calculates the particle mass and the baryon mass, sums them up, and then it gets sent back. And then what we do is for the final value, we sum up all the intermediate sums. So this, as you can tell, this works also with things like bulk velocity. However, for things like weighted averages, what you need to return is you need to return both the sum of the weight in a given grid as well as the sum of the value you're looking for times the weight. So this way you need to retain as much information as is necessary in order to calculate the final reduction. Now we call this function add quantity. we can name our quantity, in this case total mass, and it shows up in the dot quantities list of keys. We specify the function that we want, and that is this one, the combine function, which is combine total mass, and the number of return values so that it knows the shape of the values to send between different processors. And actually, there are a couple people here that have written them. I think Eve wrote one, or modified one. Steven's written a couple, Britton, Sam. So we have a number of people here that would be happy to describe how to do this and to work through one with you if you have any particular ones you're looking for. Now here's another example of bulk velocity, and the reason that I show this is that it's slightly different in the sense that the bulk velocity is the weighted average x, y, and z velocities. And so we calculate for a given data object, in this case a grid, typically a grid, sorry, the x velocity times the cell mass, y velocity times cell mass, z velocity times cell mass, and we sum those up, and we sum up our weighting field, and then we return x, v, y, v, z, v, and w, and then we write this combined bulk velocity, which accepts our data object, x, v, y, v, z, v, w, and then it actually performs the reduction operation. Now note that we return 4 values from our intermediate function, and then in our final reduction, we only return 3. But we still say that in the nret we return 4 because that's how many get returned by our intermediate kernel. So common pitfalls. We want to make sure that we have the correct array shapes in the combine function. This will actually just be a flat-out error, so you shouldn't need to worry about it unless you see it. Round-off error can be a problem. So what you need to do is you need to make sure that you're using 64-bit accumulator functions if you do any accumulation. And then field preloading can also sometimes be an issue. One thing that we try to do is we try to batch data operations, data I/O operations, so that it reads multiple grids with only a single F open and with as few F seeks as possible. This helps things like Luster and whatnot to do single strides over the data rather than multiple. And so what it'll do is it attempts to guess which fields you need and then read them all from the portions of the data set that your processor has been assigned, store them in memory until necessary, and then dump them out. And actually that is the end of the prepared portion of my talk. So let me just say thank you.